not depend on the amount of charge you put in it. Okay. What is a capacitor? Well, so far we talked about capacitance of a conductor. Let's now talk about a capacitor. Alright, let's consider a conductor carrying a charge Q. Now, if a conductor is carrying a charge Q, then it has a potential V. Therefore, its capacitance can be written as C equal to Q over V. This conductor carries a charge Q. When a charge Q is given to it, its potential is raised to V so that its capacitance C equal to Q over V. Now tell me, is it possible to increase the capacitance of this conductor? Well, you know that capacitance is Q over V. If by any means I can reduce the potential of that conductor without changing the amount of charge on it, that means in order to increase that potential back to the original value, I then need to put more charge in it. Now, in doing that, I am raising the capacitance. So, if you want to increase the capacitance, try and lower the potential of the capacitor or of the conductor. Now, can you suggest a way we can lower the potential of a conductor? This conductor now has a positive potential V. How can you reduce its potential without reducing the amount of charge on it? Well, try this. Bring a neutral conductor near the charged conductor. What happens when a neutral conductor is brought near a charged conductor? We talked about this some time ago. When a neutral conductor is brought near a charged conductor, polarization of charges will take place inside the neutral conductor. Now here I brought a neutral conductor. This is a neutral conductor. But the moment you bring a neutral conductor close to this charged conductor, what happens is inside the neutral conductor, polarization of charges will take place. What is polarization? Negative charges will move so that they reside close to the positive charged object. That means leaving the other end positively charged. You have a split of charges in the neutral conductor. As a result, the influence of these negative charges are going to be felt on our charged conductor. You know that the potential of a negative charge is negative. So, the presence of these negative charges will produce a negative potential on our charged object. The negative charges in the neutral conductor move so that they reside closer to the positively charged conductor, making the end of the neutral conductor near the charged conductor negative. You see that? Now, the accumulation of these negative charges near this positively charged object reduces the potential of this, reduces its positive potential. I suppose you can understand that argument. That means we haven't changed the amount of charge on this charged object. But by simply bringing a neutral conductor near it, we have reduced the potential. That V is now, if V prime is the new potential of this conductor, that V prime is less than the original V. That means if you now want the potential back to V, we now need to add more charges. That means we have now increased the capacitance of the conductor. Now this decrease in potential of the charged conductor without changing the amount of charge on it causes an increase in its capacitance. That means now it can hold more charges at the same potential. You see that? So we have increased the capacitance. Now, is there any way to decrease that potential still further? We can do that. You see, these positive charges are under the influence of these negative charges and these positive charges. You see, these negative charges produce a negative potential on this charge, and these positive charges produce a positive potential. That means because the negative charges are closer, the negative potential produced by the negative charges will dominate. But this effect can be increased if you can remove these positive charges from here. Now, how will we remove those positive charges? Any suggestions? Can you suggest a way we can remove these positive charges from this end of the neutral conductor? What can we do to remove them? Well, a very simple thing: ground the neutral conductor. If you ground the neutral conductor, negative charges will move from the ground, come in and neutralize those positive charges. You see that? Now, in order to increase the potential back to V, more positive charges need to be given to the conductor. Thus, the presence of the neutral conductor has increased the capacitance of our conductor. Now, what happens if the neutral conductor is grounded? Well, let's ground it. When you ground it, all the positive charges have disappeared. That means the negative potential due to these charges are now have a bigger influence on the positive potential of this conductor. The negative charges from the ground flows in to neutralize the positive charges. This leaves the neutral conductor now negatively charged. Now this lowers the positive potential of the charged conductor further. Now that means if you lower the potential, you are increasing the capacitance. You see that? Every time you lower the potential without changing the amount of charge on it, you are increasing the capacitance. Thus, how can you increase the capacitance of a conductor? The capacitance of a conductor can be increased by bringing a neutral grounded conductor near it. So this conductor, the capacitance of this conductor is much greater than its original value. Now how did we do that? By bringing a neutral grounded conductor near it. Now the capacitance of the charged conductor can be further increased. There is one more way to increase the capacitance, and that is, you see, the influence of these negative charges are transmitted to the positive charge through this intervening medium. Is that right? You see, the medium plays a part in transmitting electrical influences from one object to the other. Now, from the neutral conductor to the charged conductor, the electrical influences are conveyed or passed on through the intervening medium. Now, if the intervening medium is a much more effective medium, then the electrical influences can be conveyed more effectively. And if you can now use a proper dielectric. What's a dielectric? We talked about that in the last class. A dielectric is an insulator. If you use a proper dielectric, which will transfer the electrical influence in a much more efficient way, then we can reduce the potential of this conductor even more and increase the capacitance. You see how the various things that we have been doing to increase the capacitance. So the capacitance of this conductor can be further increased by using a proper dielectric between the two conductors, which allows electrical influences to travel through it more effectively. Now here I have a dielectric in between. Such an arrangement is called a capacitor. You see, what we have done is we tried our best. We tried all we can to increase the capacitance of this conductor. What was the first thing we did? We brought near it a neutral conductor and grounded it, and then filled the space between them by a very efficient dielectric, which will transmit the electrical influence in a much more efficient way. And this arrangement now is called a capacitor. So what is a capacitor? A capacitor is an arrangement of two conductors separated by a thin dielectric and one of them kept grounded. Well, so we have a capacitor. A capacitor has a capacitance. That means a capacitor. Can you tell me what is a capacitor used for? What is a capacitor used for? Well, if you can answer this question, what is a container used for? A container is used for storing things that it can contain. In the same way, a capacitor is used for storing electric charges. And that's the reason why we try to increase its capacitance. In other words, we want to charge more. We want to store more charges in the conductor or in the capacitor. And look at the symbol we used for a capacitor. A capacitor is represented by this symbol, two parallel lines with the connecting leads. So this kind of an arrangement is called a capacitor. Let's now look at one type of capacitor called a parallel plate capacitor. A parallel plate capacitor. Well, as the name suggests, it tells us that this is made up of two conducting plates, both made of parallel plates. In other words, here I have a metal plate, and if I have one more of these, I couldn't find one like this, so I brought a small one. But remember, the plates of a capacitor both will be the same. So if one is charged and the other is grounded and the two are separated by a proper dielectric, we have a parallel plate capacitor. In a parallel plate capacitor, the two conductors are metal plates separated by a dielectric. A dielectric is characterized by a dielectric constant, and we represent the dielectric constant by the lowercase Greek letter kappa. Kappa. Don't call it K. It looks like K, but we use this as a Greek letter. It's kappa, which has a value 1 for vacuum. But for all practical purposes, we will use the value for air also as 1. For all practical purposes, we use kappa equal to 1 for air. So if I give you a problem in which it says an air capacitor, what does it mean, an air capacitor? An air capacitor is a capacitor in which the dielectric is air. The space between the two conductors is filled with air. Now I have a table of values for kappa for different types of dielectric. Now look at this table. Air is 1.5